Okay. Hi, everyone. Thank you all for joining today for this presentation on the Gunyah Hypervisor. My name is Carl van Skyke. I'm the lead engineer for the Qualcomm Hypervisor team in Sydney, Australia. A little bit about myself. I've been working on virtualization and hypervisor technology for more than 18 years now, starting on the L4 microkernels, and we started our first experiments with virtualization on ARM 926. So of course, those CPUs didn't have any virtualization support, but now that hardware support is a standard part of ARM, the use of virtualization is becoming a lot more prevalent. So Gunyah, firstly, is an Australian word from the Sydney area where we are based, meaning shelter. So this name was appropriate given the overall goals of the project. And it's designed to be a modern and scalable virtualization framework, supporting multiple operating systems running independently, and with a strong focus on performance and security. Okay, so a question that a lot of you probably are asking, which is why a new hypervisor? Well, when we started this project to bring virtualization to mobile, we thought of the requirements, and these were firstly security. We needed a virtualization platform that was independent and isolated from all the VMs, and that included the primary VM or the Android VM on the system. And for that reason, we focused on type 1 hypervisors. Also, mobile devices are very competitive, and performance is one of the key measures that we need to maintain. And we needed some solution that wasn't going to impact performance and also was scalable to large numbers of cores for the future. We also wanted flexibility, so we wanted a solution that would target mobile, but also be usable in other areas, such as automotive or IoT, systems with very different requirements and constraints. And finally, we wanted a solution that was under a open license. So something like BSD 3 cores license was what we wanted, so that we could share the hypervisor and we could work on it unencumbered. So we looked at all the solutions out there, and nothing really fit with the requirements that we needed. So we started working on the design of a new hypervisor from scratch. So obviously the goals, performance and scalability being key. We wanted to be able to scale from single core to many cores with minimal locking. Our experience on prior hypervisors has shown that global locks and even some fine-grained locks can really impact performance quite significantly in many use cases. We also wanted really strong power management support. Obviously, the mobile devices are battery powered, and any impact on battery life is going to be a big problem. So we wanted to ensure that there's a big focus on power management. We also wanted to make sure that the core of the hypervisor was portable. Obviously, we're targeting ARM, but the core architecture is defined to be, the core code is defined to be architecture and platform independent as much as possible. In flexibility, we identified potential areas that we could use. So, mobile, IoT, automotive. And we decided that a module-based architecture was going to be important with clear interfaces, so that we could build the hypervisor with a collection of modules targeting a particular vertical. So, mobile might have a more HLOS focused architecture, where IoT auto might have a more distributed and independent virtual machines, possibly with different scheduling, other modules that can be added or removed to the system. We wanted that to be as easy as possible. So we designed, the modules needed to have clear APIs between them, so that they could be added or removed easily, or new implementations of modules written to replace others for different use cases. So the design has considered being able to create partitions in the system with different resource managers to manage your platform and memory resources. Then obviously secure isolation was another one of the primary goals. So all VMs being deprivileged. That includes the primary VM, if one exists. So all memory and IO space being isolated, all interrupts being assigned to particular VMs, and scheduling as well needed to be isolated and secure. So another design goal was to ensure that we have a secure hypercall API for the hypervisor. We looked at various different access control models, and we looked a lot at segregated capabilities. Allows us to implement a principle of least privilege, where each VM only has access and rights to the objects that it is allowed to have, and other objects in the system are inaccessible to the VM, unaddressable. And finally, we wanted to ensure that we followed industry standards as much as possible. So the virtual machines should follow ARM IP for things like the interrupt controller, timers, follow ARM APIs like PSCI, as well as support IO virtualization standards like VirtIO. So some of the features that we ended up implementing in Gunyah. So firstly, Gunyah provides the concept of partitions, and partitions are a unit of resource isolation. So physical memory of the platform is associated with a partition, and it's important that a partition doesn't mean a VM. It's a unit of resource isolation, and within one partition, a partition manager may be able to create one or more VMs from that partition's resources. It allows us to have completely independent systems concurrently on the hypervisor. So each with its own physical resources and partition managers controlling those resources. So then, of course, we have scheduling. So the hypervisor scheduler sees virtual CPUs as threads from its point of view. We have a real-time priority-based scheduler implemented using time slicing for threads with equal priorities. And the hypervisor schedules at the virtual CPU level, not the virtual machine level. So we're able to run virtual CPUs from different VMs concurrently on different physical cores. We then have address space objects. Address spaces are what are implemented by page tables, and each virtual CPU or thread is associated with an address space. So it's an interesting point that at the low level, the hypervisor doesn't really see virtual machines as an object. Virtual machine is constructed through collecting resources together. So an address space and one or more virtual CPUs come together as essentially a virtual machine. And the hypervisor has a memory management implementation. It uses objects called memory extents that are objects that represent regions of physical memory. They can be both normal memory or IO space. And associated with that, we have a memory database, which is used for tracking all physical memory in the system. It's really important. It provides us fast reverse lookup by physical address to object or page and what it's being used for currently. Being a type 1 hypervisor, Gunyah provides interrupt virtualization. Interrupt virtualization is one of the most important performance sensitive regions of the hypervisor. Of course, every interrupt that arrives will arrive in EL2 and need to be handled and forwarded to the correct VM. So one of the really important areas. And as I mentioned before, we settled on capability-based access control for the hypervisor. So the hypervisor has an object that represents a access control domain. Those are called capability spaces. So within the capability space, a capability, which is essentially a ID that user space has, well, user space being the VM kernel, that looks up objects within a capability space. So those IDs get translated through a capability space to point to objects inside of the hypervisor, and they also encode the rights that the holder of that capability has to the particular object. And it allows us to provide very flexible, fine-grained access control. And then finally, the virtual machines need to be able to communicate with each other. The types of systems that we want to build are very tightly coupled with VMs interacting closely with each other. It's fairly different to the server world, where virtual machines are for the most part independent and don't really communicate with each other than over the network. So we provide a rich set of low-level communication APIs, including doorbell interrupts between VMs, message queues for short messages copied by the hypervisor between VMs. But we also support shared memory and then more complex communication primitives like VirtIO MMIO support. So I mentioned before that the hypervisor has a partition-based resource isolation. So we do have one special VM, which is the Gunyah root VM, the resource manager in our case. So it's really responsible for system bootstrap. It creates the high-level operating system VM at boot, and assigns all the memory across to an Android VM if that is the configuration of the platform. And it's not really it's not a VM that users will directly interact with, but it provides services as well to the rest of the platform. So, for example, provides APIs for secondary VM management, and also APIs for dynamic memory management. So, lending and sharing resources between VMs at one time. So this shows a very basic architecture of a high-level OS VM, like a Linux kernel. It could be running Android. Essentially, this is a single VM architecture. So at boot time, the resource manager is the initial root VM, and it uses the Gunyah object creation APIs to dynamically set up and construct the HLOS VM. So it will create the address spaces and the virtual CPUs, interrupt controllers, assign the DDR memory to that HLOS VM, and assign any interrupts across as well. So obviously, it doesn't need to assign all the platform resources across. At the moment, in the initial version that we have released, it's assigning most of the resources other than the hypervisor's own resources across to the HLOS. So all the IO memory and interrupts. So all your regular device drivers for your platform can run unmodified as pass-through under the system. So as for platform support, right now we have support for running on AR64 with VHE. So that's on v8.2. We support the QEMU simulator. So that's running on the generic Virt machine model in EL2 with a JIC-v3 interrupt controller. That's running with JIC-v3 virtualization, and all interrupts handled at EL2 and delivered to the primary VM. We also support PSCI in platform coordinated mode, and we have a low power timer driver for waking up VMs waking up VMs on resume. And we also are currently working on Qualcomm RB5 support. That's still a work in progress. So with that, you'll be able to run Gunyah on Qualcomm hardware directly. So building and running Gunyah. So you can get Gunyah today from our quick GitHub account. That's github.com/quick/Gunyah-hypervisor. We have all the documentation there on downloading, configuring, building, and running Gunyah on a QEMU virtual platform. So Gunyah's got a Python-based build system. It is designed around the flexibility of the modules that I mentioned before. So the build system, in the build configuration, you specify which modules you want to use for your configuration. And the build system brings together those. Each module defines the types that it uses and an abstract syntax language. It also provides its set of APIs, and modules can define events and register for events. For provided by other modules. So it allows modules to be flexibly added or removed from a configuration, and new modules replaced. So if you wanted to build a new scheduler, you could write a new scheduler module that provides the scheduling events and registers for the context switching and interruption modules events for blocking and unblocking threads. So then we also have the resource manager code and a simple C runtime based on muzzle libc. So the resource manager is an OS-less C application running in a bare metal VM. And finally, we have a boot image generation tool that takes the hypervisor image and the resource manager and combines those two together into your minimal boot image that you can load into memory using QEMU command line, past the hypervisor boot image as the kernel. Right now on QEMU, you also have to load the Linux kernel for the HLOS VM. You do that using additional load arguments on the QEMU command line. So, as for booting, Gunyah expects to be started in Yield 2 by a bootloader. With QEMU, we don't have any on-target bootloader. QEMU loads the image directly. And then after the hypervisor init, the resource manager is started, and it dynamically creates the primary VM. And on QEMU, we will jump to the Linux kernel image that was also loaded by QEMU on the command line. We have a bunch of hard coding at the moment for where to find the kernel images. For example, we use QEMU to load the hypervisor VM L file, but then we also, on the command line, we are passing the device tree address, the kernel, and an initial RAM disk. And those addresses are currently being hard-coded. In the future, we'll be looking at a more dynamic configuration where these can be passed in through from the command line. So some of the next steps for the Gunyah project. So obviously, right now the Gunyah that has been contributed is running only a single Linux VM on QEMU. We are working on the ability to do dynamic secondary VM loading, so runtime creation of additional VMs through the resource manager APIs. We'll also be adding VirtIO support for those VMs. So the secondary VMs using a VirtIO frontend can access storage through a backend provided by the primary Linux VM with the storage drivers. We'll also be looking at making it a bit more flexible, removing some of the hard coding of where the resource manager expects the Linux kernel to be loaded and how much memory is in the target. And we also have a lot of other improvements across the board that we have been working on, and hoping to contribute those as soon as we can. Well, thank you everyone for attending today. I hope you'll all be able to in a bit of spare time, take a look and download Gunyah and give it a try. One of our goals is to foster an open source community around Gunyah. So again, please try it out, and we look forward to your questions and comments.